Hello friends, I welcome you to the lecture on integro-differential equations. Linear integro-differential equation is an equation of the form a naught x into by n x. By n x is the nth derivative of by with respect to x plus a1 x by n minus 1 x and so on a n x into by x plus sigma s is equal to m equal to 0 to s 0 to x km xt by m dt equal to fx, where a naught, a1, an x and fx km xt m varying from 0 to s are known functions and yx is the unknown function. Further, we are given the conditions on y, by 0 equal to y naught, by dash 0 equal to by naught dash and so on by n minus 1 0 equal to by naught n minus 1. These are the initial conditions. Let us assume that the coefficients akx of the integro-differential equation, these coefficients akx are constants. Let us denote the coefficients akx by the constant ak for k equal to 0, 1, 2 and so on up to n, and let us assume that the kernel km xt is equal to km x minus t for all values of m, that is 0, 1, 2 and so on up to s. That is, all the km's depend on the difference x minus t of arguments. Without any loss of generality, we can assume a naught equal to 1, because if it is not 1, we can divide the equation by a naught. So when we assume a naught equal to 1, then the equation 1 reduces to this form. So we have by n x, another derivative of by with respect to x, plus a1 n minus 1 other derivative of by with respect to x and so on a n by x, and then sigma m equal to 0 to s, this integral equal to fx. a1, a2, an are constants. Now let us assume that the Laplace transform of fx is fs. So by definition of Laplace transform, fs is equal to integral 0 to infinity e to the power minus sx into fx dx, and Laplace transform of kmx we assume as km bar s. So km bar s is equal to integral 0 to infinity e to the power minus sx into kmx dx, where m is equal to 0, 1, 2 and so on up to s. Further, let us assume that the Laplace transform of the unknown function by x be by s. So we assume by s equal to integral 0 to infinity e to the power minus sx into by x dx. Now what we do is we take the Laplace transform of both sides of the equation 2 and recall the formula for the Laplace transform of the nth derivative of by x. So Laplace transform of nth derivative of by x is given by s to the power n Laplace transform of by x minus Sn minus 1 by at 0 minus Sn minus 2 by dash at 0 and so on minus by n minus 1 at 0. Now according to our hypothesis assumption, this is s to the power n, Laplace transform of by x is by s. So we have by s minus Sn minus 1 by 0 is by naught minus Sn minus 2 by naught dash and so on minus by naught n minus 1. So let us substitute this value. When we take the Laplace transform of by nx, we get s to the power n by s minus Sn minus 1 by naught minus Sn minus 2 by naught dash and so on minus by naught n minus 1, and then a1 times Laplace transform of n minus 1 of the derivative of by with respect to x. So we have s to the power n minus 1 by s minus s to the power n minus 2 by naught and so on by naught n minus 2 and so on. We have an Laplace transform of by x, which is which is by s, so an into by s, and then we have sigma m equal to 0 to s Laplace transform of this integral. So we have sigma m equal to 0 to s Laplace transform of integral 0 to x. We had 0 to x km x minus t into by mt dt. Now let us write the Laplace transform of. So Laplace transform of integral 0 to x km x t x minus t into by mt dt we apply convolution theorem here. Laplace transform of kmx into Laplace transform of by mx. So by applying convolution theorem, Laplace transform of integral 0 to x kmx minus t by mt dt is Laplace transform of kmx into Laplace transform of mx. Now this is km bar s, and this is again we apply the formula. So s to the power m by s minus s to the power m minus 1, and then we have by 0 which is by naught, s to the power m minus 2 by naught dash, and so on, minus s to the power m minus 1. So we will get sigma m equal to 0 to s km bar s into sm by s in minus sm minus 1 by naught, and so on by naught m minus 1, and Laplace transform of the right side is fx. Laplace transform of fx we have assumed as fs, so we get fs here. Now what we do is we collect the coefficient of y(s). So when we collect the coefficient of y(s), what we have, s to the power n, then a1 times s to the power n minus 1, and then and so on a naught is and so on an we have, and then sigma m equal to 0 to s km bar s into s to the power m. The remaining thing is a function of s, we can write it as as. So we get the value of y(s) from here. As is a known function of s, so we determine y(s) from this equation 3, and then take the inverse Laplace transform. Inverse Laplace transform of y(s) when we do, we obtain the desired function by x, which is the solution of the equation 1. For example, let us consider the integro-differential equation phi double dash x plus integral 0 to x e to the power 2 times x minus t phi dash t dt equal to e to the power 2x. Phi 0 is equal to phi dash 0 equal to 0. So it is an integro-differential equation. We are given the initial conditions, phi 0 equal to 0, phi dash 0 equal to 0, and phi is the unknown function. So let us take the Laplace transform of this equation. So Laplace transform of phi double dash x plus Laplace transform of integral 0 to x e to the power 2 times x minus t into phi dash t dt equal to Laplace transform of e to the power 2x. Now Laplace transform of phi double dash x is s to the power 2 phi s minus s times phi 0 minus phi dash 0 plus by convolution theorem Laplace transform of integral 0 to x e to the power 2 times x minus t phi dash t dt is Laplace transform of e to the power 2x into Laplace transform of phi dash x, and Laplace transform of e to the power 2x is 1 over s minus 2. So we have s square phi s, phi 0 is 0, phi dash 0 is 0, and Laplace transform of e to the power 2x is 1 over s minus 2. Laplace transform of phi dash x is s phi s minus phi 0 equal to 1 over s minus 2. Phi 0 is 0, so we get s square plus s over s minus 2 phi s equal to 1 over s minus 2, and what we get is, we can simplify this. So s square into s minus 2, so phi s equal to one over s square into s minus 2 plus s, and what we get is 1 over s into s minus 1 whole square, because this is s cube minus 2s square plus s, so we can take s common, and this is 1 over s into s minus 1 whole square. We can break it into partial fractions, a over s, b over s minus 1, c over s minus 1 square, and we can determine the values of ABC very easily from here. When we determine the values of ABC, we notice that this is phi s is 1 over s into s minus 1 whole square, this is 1 over s minus 1 over s minus 1 plus 1 over s minus 1 whole square. So this a comes out to be 1, and b is minus 1, c is 1. We can easily find those values. So this is 1 over s plus 1 over s minus 1 minus 1 over s minus 1 and 1 over s minus 1 whole square. Now let us take the inverse Laplace transform. So inverse Laplace transform of phi s equal to inverse Laplace transform of 1 over s minus inverse Laplace transform of 1 over s minus 1 plus inverse Laplace transform of 1 over s minus 1 whole square. Now inverse Laplace transform of 1 over s is 1, and inverse Laplace transform of 1 over s minus 1 is e to the power x. We have to find the inverse Laplace transform of 1 over s minus 1 whole square. So for that, let us recall the formula. If Laplace transform of ft is equal to fs, then Laplace transform of tft is minus d over ds of fs. So we know that Laplace transform of e to the power t is 1 over s minus 1. So Laplace transform of t times e to the power t is minus d over ds of 1 over s minus 1. So this is minus 1 over s minus 1 whole square. So we get 1 over s minus 1 whole square. So inverse Laplace transform of 1 over s minus 1 whole square is t e to the power t. Here we will have x e to the power x. So now inverse Laplace transform of phi s is phi x. So we get phi x as 1 minus e to the power x plus x e to the power x, which is the solution of the integro-differential equation. We can check that phi 0 is 0 here. Phi 0 is equal to 0 because it is 1 minus 1 plus 0, and we can also see that phi dash 0 is 0. So it is the solution of the given integro-differential equation, 1 minus e to the power x plus x e to the power x. Another example we can take, say y dash t equal to sin x, y dash t equal to sin t plus integral 0 to t by t minus x cos x dx and y0 is equal to 0. So here again let us assume that Laplace transform by t is by s, and then let us take the Laplace transform of both sides of the given equation. So Laplace transform of by dash t will be s by s minus by 0, and Laplace transform of sin t is 1 over s square plus 1 plus Laplace transform of 0 to t by t minus x into cos x dx. Now by 0 is given as 0, so s by s 1 over s square plus 1. Here we apply the convolution theorem, so Laplace transform of by t into Laplace transform of cos t. So this is 1 over s square plus 1 plus Laplace transform by t is by s into s over s square plus 1. We then simplify and get the value of by s from here. So s minus s upon s square plus 1 into by s is equal to 1 over s square plus 1. So what we will get, s cube plus s we get this r by s equal to 1 over s cube. Let us take inverse Laplace transform. Now recall the formula that Laplace transform of t to the power n, if n is a positive integer, it is n factorial divided by s to the power n plus 1. So here we have Laplace transform of inverse Laplace transform of 1 over s cube will be t square divided by 2 factorial r t square by 2. So by t, thus by t is equal to t square by 2, and it is the solution of the given integro-differential equation. So this is what we have here, by t equal to t square by 2. Okay, let us take one more example of an integro-differential equation, by dash t equal to t plus integral 0 to t by t minus x cos x dx, where by at t equal to 0 is equal to 4. So let us see, by dash t is equal to t plus integral 0 to t by t minus x into cos x dx, and we are given by 0 equal to 4. So let us take Laplace transform of both sides of this equation. So Laplace transform of by dash t equal to Laplace transform of t plus Laplace transform of integral 0 to t by t minus x into cos x dx. Now let us recall the formula for the Laplace transform of by dash t. So Laplace transform by dash t is s by s minus by 0. By s is Laplace transform of by t, and then Laplace transform of t is 1 over s square plus by convolution theorem Laplace transform of integral 0 to t by t minus x cos x dx is Laplace transform of by x into Laplace transform of, or rather I can say by t, and then Laplace transform of cos t. So this is s by s minus 4, because by 0 equal to 4, 1 by s square, then we have by s, and then we have s over s square plus 1. So let us collect the coefficient of by s times s minus s upon s square plus 1 equal to 1 upon s square plus 4. This is by s times s cube plus s minus s, so s cube upon s square plus 1 equal to 4s square plus 1 divided by s square, and so we have by s equal to 4s square plus 1 into s square plus 1 divided by s to the power 5. Let us multiply in the numerator. We have 4s4 plus s square plus 4s square plus 1 divided by s to the power 5, and which is nothing but 4 by s, 5s square by s to the power 5, so 5 by s cube, and then 1 by s to the power 5. So this is by s. Now let us recall again the formula. Laplace transform of t to the power n is n factorial divided by s to the power n plus 1. So by that Laplace transform of 1 is equal to 1 over s. Laplace transform of t square is 2 upon 2 factorial upon s cube. Laplace transform of t to the power 4 equal to 4 factorial divided by s to the power 5. So applying these formulas, inverse Laplace transform of by s will be 4 times inverse Laplace transform of 1 by s plus 5 times inverse Laplace transform of 1 by s cube plus inverse Laplace transform of 1 by s to the power 5, and this will be equal to 4 plus 1 by inverse Laplace transform of 1 by s cube will be t square by 2. So 5 by 2 t square, inverse Laplace transform 1 by s5 will be t4 by 4 factorial, so t4 by 24, and inverse Laplace transform of by s is by t, so we get the solution as we have by t equal to 4 plus 5 by 2 t square plus t4 by 24, which is the required solution of the given integro-differential equation. This is what I had to say in this lecture. Thank you very much for your attention.